And this is the receiver of RDT 2.1. You see, similarly, the number of states and transitions also doubled. We borrow the technique I used to describe the sender side. So the line in the middle here actually indicates the upper left and the lower right. They are the mirror of each other. The difference is just that the upper left is handling data sequence number 0, expecting data sequence number 0. And the lower right expecting and handling sequence number 1. And then we propose that we walk through the state machine this way. First, assuming that there are not going to be any data corruptions nor the ACNAC corruptions, meaning things are going perfectly. At the beginning, receiver will start from the initial state, wait for packet 0 coming from below. And nothing's going to be wrong there, therefore it will be triggering, this condition, this transition. Okay, so receiving a packet, no corruption, and it's carrying sequence number 0 here. Okay, expecting 0, carrying sequence number 0, perfect. Let's extract the data, pass it up to the application layer, generate the add packet, but this time what? Including the checksum. So this is coded in RDT 2.1 because we are now assuming also ACNAC could be corrupted. So checksum here is to enable the data center to be able to check whether the ACK packet or the NAC packet is corrupted. So that ACK packet with the checksum will be generated and sent back. All right, straightforward. And we move to the new state, wait for 0 from below. Similarly, we'll be getting a packet from below, receive RDT, and not corrupted, and carrying the expected sequence number 1. Cool, happy again. Extract data out of the packet, pass it up to the application layer, generating an ACK with checksum, send it back. Upon finishing all these actions, we take the transition. Receiver here, go back to wait for 0 from below. If another packet comes in, not corrupted, carrying sequence number 0, again happy, take the transition, wait for 1 below. And this will go on and on and on and on and on. And when there's no data corruption, when there's no ACNAC corruption. Now, what if there's data corruption in RDT 2.0? That's where we begin to see these transitions showing in the receiver side of RDT 2.0. This is the case when we are expecting 1, but we get the corrupted data. Then we say, hey, the data is corrupted. Generate a negative acknowledgement, but hey, in RDT 2.1, we do need to include the checksum and send it back to the data center. Similarly here, if we're expecting 0, receiving a packet, it's corrupted. Generate the NAC, send it back to the data center. Okay, so these two transitions we know well. Okay, they have already appeared in RDT 2.0. The two transitions remaining, this one and this one here. So this guy and this guy here. Okay. Just like these two, very similar. These two, very similar. They are actually very similar as well. So let's focus on this guy here. So this is the case when we are waiting for packet 0 to arrive. We did get a packet, it's not corrupted, but wrong sequence number. How can this be happening? Well, then this must be because, hey, sequence 1 here has already been received earlier. That's why we've already moved on to wait for 0. Now, receiver here, receiving 1, will be also sending an ACK back to the data center. But the data center there finds that packet corrupted. Okay, that's when the sender retransmit sequence 1, thinking, I'm not sure, I'll just retransmit. And therefore, we get a duplicate packet here. All right, so if that's a duplicate, no, that's not extract packet, that's not deliver, again, the same thing up to the application layer. So you see here, the only actions we'll be taking is just not extracting data, not passing up to the application layer, but only to generate the acknowledgement and send it back to the sender. Now, is it necessary to generate another ACK? It is, isn't it? Because the previous ACK here, it was corrupted. So sender there is just gonna think that data might not be there. Data might not be there. To be safe, let's just retransmit. So this ACK here is actually crucial, so that the sender, hopefully the second time, gets the ACK all right and they can move on to what? Wait for call from above for packet 0, because it's now stuck at the packet 1's feedback. So, this is RDT 2.1. Now let's use a couple of very simple scenarios to demonstrate how the sender and the receiver interact. So this is RDT 2.1, no error case, and the scenario is simply first to send one packet, and then second, continue and send yet another packet. Okay. So our goal is to find out all the transitions being triggered until it reaches the steady state. Now, in order to find out what transitions each of these finite state machines will be taking, we need to know the starting state. Now, at the beginning of the sender, it's going to start from the initial state. So the starting state will be the initial state for the first transition. Similarly for the receiver, this is the initial state. Therefore, the starting state of the first transition at the receiver side is going to be also the initial state. Now, event is the send one packet. Now, we're here at the starting state to determine what transitions to take. Let's check out what the transitions are. Well, starting from this state, there's only one possibility, which is T1. And it happens to be what? Getting a call from above, which is to send one packet. So, obviously, the first transition we'll be taking is at the sender side, and it's T1. And it matches this event here, and it's gonna complete all the actions listed here, which is to generate data packet 0 and send it out. At this point, sender here enters the wait for ACK or NACK 0 state, right? So, very important, before you determine what transition to take next, what is the starting state right now? What are the possibilities? Are there multiple transitions one can take from the starting state? If there are, be careful. What is the triggering event? Okay, so pick the transition that's matching the triggering event. And then take the actions, and then finish the transition, and land on the ending state. All right, so let me repeat. Starting state, possible transitions, match the triggering event, and then land on the ending state. So now we're done with T1. So the result of T1 is there's a packet being generated, isn't it? And that's going to arrive at the receiver side. Receiver side, currently here. So this is going to be the starting state of the next transition being triggered. And it's receiving a packet from below. So let's see, what are the possible transitions? 1, 2, 3, because all 3 of them starts from the state here. Now, event is, we receive a packet, definitely. Okay. So all transitions is triggered by receiving a packet. But exactly which one is triggered depends on checking whether the packet is corrupted or not. And we're assuming no error, so this one is not possible. So this one passed to this point, this one passed to this point, but there's one more check. Is the packet sequence number 0 or sequence number 1? Here, we are generating sequence number 0, therefore, eventually this transition waits. And so we'll be taking T11 over here and taking all these actions and moving the receiver to this state, wait for 1 from below. And now next, right, over here, the receiver is generating an ACK packet and it's being sent back. So that's gonna trigger an ACK packet arriving back at the sender. So sender here currently at the wait for ACK or NAC 0 state. See, there are 2 possible transitions. So which of these matches the ACK packet with no error? Yeah, this one here. No error, and it's ACK packet. So we'll be taking T2 and finish all the action here, which is doing nothing, and enter the wait for call 1 from above state. So sender here goes to this state. And there's nothing to be done here. No more packet being generated flying back to the receiver, so we kind of stabilize this right here. So sender here, stop here. Receiver, stop here. Okay? And in the process, we take 3 transitions. First one is T1 at the sender side. Second is what? T11 at the receiver side. And the third being T2 at the sender side. And now let's move on with scenario 2. So we'll continue from S1. Well, we actually finish S1 here and here for respectively the sender and receiver. Now we'll be sending yet another packet. So sender here gets call from above, RDT send. Therefore, these actions will be taken and we'll follow through T3, that transition, and enter the wait for ACK NAC 1 state. Now this is going to generate packet data 1, and this is going to go to the receiver, which is sitting right here, wait for 1 from below. There are 3 possible transitions stemming from the state here. And which one does a receiver take? Well, receive, 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 and this is packet 1 not corrupted, so not corrupted, not corrupted. So this one is quickly out, and it's packet 1, so yeah, this one here wins. Therefore, we take T12, take all these actions and go to the wait for 0 from below state here for the receiver. Now an ACK packet will be generated, and this is gonna go back, yeah, to the receiver, which is currently waiting for ACK or NAC 1. And it's getting an ACK for 1. It's going to do nothing but follow through T4 and enter the wait for call 0 from above. So overall, sender here takes T3, generates data, therefore calls T12 at the receiver side, generates ACK, and therefore calls T4 at the sender. And finally, both of them stabilizes, yeah, because of no action here in the last transition, and sender goes back to wait for call from above, receiver goes back to wait for 0 from below. Now, this slide is called discussion, but what it does is really the summary of 2.1. So at the sender side, what's being special is this. Sender checks whether the ACK/NAC is corrupted. Okay? Now, in order to prevent having duplicate packets, the sender side now also assign a sequence number to the data packet sent. So it's either 0 or 1. And in order to track, okay, data packets carrying the sequence number, there are now twice the amount of states and twice the amount of the transitions. So the states somehow need to remember what is the expected sequence number. Receiver side, the primary function is to avoid receiving duplicate packets. So it would check the sequence number, whether it's a repeating sequence number. In that case, the packet is a duplicate. Okay? If that is the case, the data will not be extracted, passed up to the application. It's just going to be discarded. But be careful. Receiver here seeing a duplicate, although not extracting data, not passing it up to the application, it will still what? Send an ACK out again. All right. Why? Because the former ACK or NACK being sent back to the sender. Yeah, only the sender knows whether the packet is corrupted. And if it's corrupted, the sender doesn't even know whether it's an ACK or NACK. So sender there is trying to be fuzzy and do the best thing that he can do, which is to repeat sending the data that has been previously sent. So receiver here, okay, needs to be more considerate. In case it's a duplicate packet, send back the ACK again, just in case it's an ACK packet being sent back and it's corrupted at the sender. Now at least the sender will be informed. Everything is okay and move on.